All right. Well, folks, we're going to get started here, do a quick little design debrief. Want to thank you guys, and thank you for putting up with the weather. Michigan can be a little fickle sometimes, and for those of you who are, I know I myself have grown a little bit more accustomed to a Southern California type of weather patterns, and so it's been a little challenging for me, even though I'm actually lived here for a good while. Want to, how about a round of applause just for all the participants so far, all the cars we've seen, and it's pretty impressive stuff. And then, so basically for the design event, myself, Tony Licio, Steve Fox, and then Bill Riley, we're the three of us have been, working to try to provide a decent environment for you guys, decent competition, and you guys, we're here because we love seeing the cars and talking to you and working with you, and you guys did not disappoint us again this year. It was great. But we're gonna quickly just walk through some of the best of what we saw. Before I get started, I guess I want to thank Bosch. Bosch is the official sponsor for the design event this year. They provided our shirts, help fund this competition, help make this competition what it is. So we want to thank our event sponsor Bosch for that. So I guess we should get to the cars. Third place. Our third place car this year is RIT. The RIT car weighed in this year at 426 pounds. It is a monocoque construction, obviously with an extensive aero package, powered by a turbocharged Yamaha 450. It runs E85 fuel and is on 10-inch wheels. This year, all three of our cars actually are on 10-inch wheels, which is not a requirement to be a top level car, but it is a common trend across at least these three. We did have a couple cars that were 13-inch wheels cars in the finals, but these are the three that ended up on top. In terms of a couple of, almost gave it away. A couple of just interesting items. This team, a lot of teams do this. Most of the good teams do this, but they did use a points analysis, as a design tool to help guide their design. Basically breaking down, each event into, the possible points that they can win, and then, design parameters, how those would impact, the points won. If you want to win overall, you kind of need to know how you're going to get there. So this is a good practice, and we again applaud their effort for doing it and the quality of job that they did in that. Next, they did some good testing, looking at the composite material properties. Again, quite often, teams will assume isotropic material properties, which is clearly false for composites. And this team did a good job of doing physical testing and using that data to basically field their actual design. Next, engine stiffness. A lot of teams kind of treat the engine, when they're using the engine as a stressed member, almost treat it like an infinitely stiff object. Clearly, it's not. They did some testing to basically figure out what the appropriate stiffness should be for that element in their frame, in their structure. So kudos there. That said, I guess one little minor point of criticism here is that the judges overall would have liked to have seen a little bit more validation of the total chassis structure in the end. It's one of the most often overlooked or at least under conducted aspects of the design process, that being the full validation leg, and it's important not just to ensure that you actually hit your targets, but it's also important to be able to go back and ground your models, so when you go back and follow in future years or whatever to do further iterations, you know that your starting point is good. It'll also help you as you're working to correlate the model. You'll find out where your deficiencies in modeling are, let you correct them, and which is it'll help, just direct, future activities. You'll basically understand how the model works better. Therefore, the next time you go to implement it, you'll be able to do so more effectively. They used proof testing for bonded joints. Again, this is something that not a lot of teams necessarily do. There might be some initial testing just to, like, well, what's the shear strength going to be on this type of joint? Then just use those numbers and keep applying them across everything. But given that, that bonding is such a, or at least can be, a very, very sensitive process to, or very process sensitive, cleanliness, surface roughness, and all these kinds of things all can impact the bond quality. So proof testing is quick and easy and pretty important to ensure that you've got quality parts. Compliance targets. Again, there's a number of teams that actually we'd like to see more teams actually factor in compliance into their actual designs. And develop sensitivities. Camber stiffness, toe stiffness, these kinds of things, and actually, factor them in. And then, again, ideally, you're going to be using, real hard data. Actually collect some data to confirm that your estimations and whatever are accurate. And then another area here where they use testing to help their design. If you notice, there's actually kind of a theme here. A lot of it is very testing based. Some of this testing happened before the design was done. Some of this testing was happened, during and after. Testing is kind of an ongoing process. And in this case, not only just did they do testing just to confirm that, okay, our axles are okay. They actually, developed, got some learnings from it and then applied it and did some design iterations as a result. Again, so, not just testing for the sake of testing, but testing to inform design decisions. Next, hardware in the loop testing. This is something that, again, it's important to, I guess, if you want to be able to do rapid, iterations on software and whatnot. It's often hard to do that, on the vehicle. By setting up like a hardware in the loop test rack, you can, set up, design cases, and you can just iterate quickly through, software validation and that kind of thing. So this team, did some of that. Especially specifically with respect to their dash, and I'm sure they yielded some benefits. Another testing-related item, the test-derived targets for brake temperatures, brake pads. Again, a lot of brake pads, the brake system is one of those systems where temperature significantly impacts the output, the performance. So unless you know what those parameters are, it's kind of hard to do the design and develop targets for them. So again, kudos here. And then again, on the compliance level, just to give kind of an indication as to some of the the level of depth for their analysis and compliance, they actually did the calculations, the old hoop stress on the brake lines, and factored that in as well. Again, a lot of teams tend to they might do some caliper analysis, FEA on the calipers and see what the compliance is there. But and again, if you want to look at the full system, you need to consider all areas. And in this case, the brake lines are still a piece of that. All right, so that concludes the quick little talk about RIT. Let's give RIT a round of applause. All righty. So, our second place car is ETS. Wait till you hear who won. Okay, so the ETS car is a 325-pound little powerhouse, running basically a special designed, kind of a student design block based off of a Yamaha 450, supercharged. It's a slick little piece of engineering. It's running E85 and is also on 10-inch wheels. All right. They displayed an excellent knowledge of composite analysis techniques. Again, composites can be a little tricky to analyze correctly. But they displayed, not only did they execute well, but they had a good understanding for the fundamentals that that go into those simulations. As one of the as noted kind of before, some of the process sensitivities with bonding, put together composite structures. There's definitely some significant process sensitivities, and we really appreciated the fact that in terms of some of their material selections, they actually considered trying to make the process a little bit more robust, specifically to bond prep. Again, this is something that for example, in the aerospace industry, we struggle with, which is why we have to do a lot of, post-assembly testing and whatnot on our stuff just to make sure that we're good, just because it is hard getting good bond prep, surface prep, and all that, and so good on them for putting some effort towards that. They also, with their bonded joints, a number of the bonded joints, they also would include a rivet or some other sort of mechanical connection, and while the mechanical connections may not be provide the required strength to actually, suit the true purpose, they should at least hold the assembly together so that you don't have complete separation. So again, it's not so much a performance thing as it is just kind of a safety redundancy thing. So a good practice that they've been employing. In terms of their assembly process, and I should say, this is more of a project management standpoint, but they had their car pretty well broken down and defined into, it was somewhere around like 800 individual steps for the manufacturing process, which is it's what you have to do if you want to very, very accurately track your progress, know where you are, see where you are relative to the schedule and whatnot. As many of you I'm sure have learned, this is as much of a project management competition as it is as an engineering competition. It doesn't matter how great your designs are and how clean they are if you can't get the drawings done in time to get them machined and manufactured, get your car assembled, begin your testing, go through your testing phases. I mean, these are all things that building these cars takes a lot longer than I think most people would ever imagine. I'm sure that you guys are in a position where you can kind of attest to that. I'm sure, I don't know how many of you were probably planning on, we're going to be driving by January 1st, and, well, some of you were probably riding in the back of a trailer, bouncing on the road, trying to put things together still. So it is important to get the project management stuff right, and so this is one of the things, they did a good job of tracking and documenting, this aspect. In terms of monocoque structures, sometimes I definitely can be, personally a little bit, sometimes a little bit critical on the monocoques. I just, I keep asking the question why. I want to make sure that, there is definitely some very, very good reasons, but I want to make sure that, if teams aren't actually producing a light enough structure, then it's like, well, why did you bother? Maybe you should just do it, take the easier path and, do a tube frame. But this is an example of a chassis where they did it right. And they made it light, and it's strong, it's light, it's stiff. It's a pretty awesome piece of composite, example of composite engineering. So this is a case where, yeah, they did it right. Another kind of interesting things. This is kind of a part of a project management aspect. They had kind of set defined design standards. And as a part of that, they also had some defined standard parts. Again, in order to make the job of building one of these cars is hard enough as it is. And if you want to make it harder, the best way to do that is just make every part absolutely unique and have everybody running off in their own direction, kind of doing their own thing. But by clearly kind of defining, and providing some structure to the design process, and to how drawings should look, and all the details that can impede manufacturing, by nailing down some rules early on. I think again it helps you stay on schedule, helps ensure that parts quality is there, and that things go together in the end when you expect them to. One of the things that we'll often do in design, the reason we do this is because it's in the rules. It is a rule stipulated thing. Is that the cars. All cars should be capable of, basically accommodating from the 95th percentile male to the 5th percentile female. So we make an attempt to kind of just, verify this a little bit, and we'll throw in this year's case, I was the big guy. I guess I'm not what I lack in height, I make up for in girth, I think. So I jumped in each of the cars. We also had a volunteer that represented the fifth percentile female to kind of see how she fit. And of the cars, this was by far the most comfortable car, without question. And not just kind of arbitrarily. I mean, it was pretty obvious that with their composite tub, they made some clearance, for the elbows, so I wasn't, driving to drive with my arms pinched against my body and all that. Likewise, the pedal travel. They actually with the fifth percentile female in there, they actually had a little bit of extra room that they could have slid things forward. So they could have accommodated, I don't know, maybe a third percentile female or something. So good for them for actually designing a car that anybody could drive. Again, not so important on the track here in Michigan, but it does reflect the fact that they tried to be true to the intent of the competition and meet the rules therein. In general, very clean chassis. Again, kind of coming back to the composites and the quality of job they did there. They used FiberSim to basically measure assess the material properties as laid up. As you're using the composite fabrics, as long as things are planar or you've got just a simple bend, everything's fine. But once you start, once you start molding around a complex shape, compound, angles, whatever, the fibers start to, stretch or compress and do some weird stuff. And by doing the analysis on the as assembled, geometries, you're gonna have something that's far more representative. So it's a bunch of extra work, but it's good stuff, and we're glad that they did it. Another interesting thing is did some sound level mapping on the back of the car. Again, not something that's necessarily a requirement in order to for performance out on the track, but it is something that is going to yield some rewards in terms of ensuring that they actually hit the sound targets, sound requirements. And again, it's as judges, we appreciate it when rules are adhered to. I mean, obviously, we also appreciate it when certain rules kind of get, artistically interpreted, in terms of trying to add performance or, those kinds of things. But at the same time, there's certain just fundamental things that it's kind of nice to see people just, pay some attention to and make ensuring compliance. I guess the last thing to note here is just excellent job on the oiling system, and yeah. So this brings us to our first place car. Oh, I'm sorry. Yes, thank you. Yes, let's hear a round of applause for ETS. All right, this brings us to Stuttgart, this 383-pound masterpiece over here. Well, one of the aspects that we, design judges try to do is kind of, we have you, fill out the spec sheets and submit them in order for us to get a snapshot of the cars before you actually arrive on site. In a lot of ways, it's your team's resume. In a way for the design judges get to know your team and what you're going to be bringing to show us here shortly. We try to use that not only to learn more about the car and kind of get a advanced start the judging process a little early, but also as a means for kind of holding you accountable for it's like, well, we say we're going to bring a 200-pound car and it shows up weighing 400 pounds. It's like, okay, something clearly went wrong. This is actually a car that came in a little bit underweight from what the spec sheet said. I think was it 9 pounds or something like that underweight. Now, Bill and I, as we were chatting about it, were pretty impressed until we realized that this car was actually built before the spec sheet was submitted. So they kind of knew the answer. They didn't have to estimate. But at any rate, it's I don't know. Maybe it's more funny to me than it is to you guys. Sorry. So this car is again another composite monocoque. Very, very extensive and well executed aero package. The one of the more impressive aero packages that we saw this weekend, if not the most impressive. It runs a 4-cylinder R6, naturally aspirated off a E85, and is also a 10.5-inch wheel car. So they had, and it, the tub, again, a lot of good work in terms of the analysis and testing, correlating. You design, you simulate, you test. And closing that loop is very, very important. In terms of just overall workmanship and craftsmanship, ETS is known for bringing very, very beautiful cars. This year's car is no exception, but the Stuttgart car is definitely pretty amazing. I mean, it's hard not to look at that thing and be impressed, and you just want to touch it. And it's just such a beautiful car. Everything's just done so nicely. Again, the aero correlation and validation. Again, a lot of testing. For roll, pitch, yaw, ride height. I mean, the aero. The simple model of just plucking something in a wind tunnel and just seeing how the air flows over it, measuring lift and drag, that's a good starting point. But in order to truly characterize how the vehicle is going to behave, and have the proper input in order to design the suspension, and chassis and the whole system to work well, you really need to know how it's going to function, at different attitudes, pitch, ride height, all these different things, which can have pretty significant impacts on what happens to not only just the level of downforce, but where does the center pressure move and all that kind of thing. And ultimately you want to be using that information, as you can having the systems, the systems that interact, that being the suspension and the aero package, in order to build a system that's going to maximize the overall vehicle performance. And this is something that they've done a pretty amazing job at. A number of conversations over the weekend about this car and about what they've done this way in terms of just how impressed the judges were. And we just want to encourage all you to attempt to do the same. Keep working in this direction. Again, another team that had an excellent example of doing the points sensitivities. And in this case, they tied it directly to lap time simulations. Again, a pound cost me, tenth of a second. These kinds of things. It's important to have it. They're all models. They're not going to be 100% perfect, but it at least gives you a good starting point to try to make some decisions and figure out what's going to be important to your team and what your strategy is going to be. Again, a notable amount of brake dyno work. They actually did full endurance runs and to simulate again full events on the brake dynos to again capture brake performance over the course of the full event. Ensure that the durability is going to be there. Is the pad's going to live. What happens to our brake temps. All these kinds of things. Just to ensure that the full system will perform as expected and to meet the needs of the car. The tub itself. A number of times, you'll see people walking around with a quarter kind of tapping composites, and it's actually a pretty decent test for, looking for, bad bonds and that kind of thing. But they did some shearography, and employed some other NDT non-destructive test techniques, to basically inspect the chassis, which is pretty wise. Again, there's a lot going on there. There's a lot of process sensitivity, and if you've got a bad spot or a delam or forgot to pull off some peel ply or I don't know something, you want to know about it before you start truly stressing the chassis. It's a heck of a lot easier to fix, a little bad spot, before something bad happens than after. For post testing, there's a number of teams that find ways to get on 4 posters. For some teams, it ends up being kind of a check the box or confirm that our ride frequencies are right or something like that. But this was an example where they used the data to solve a problem. I honestly don't know specifically what kind of challenge they were facing with the third spring, but apparently by via some testing on the 4 poster, they were able to resolve it and use that as a useful tool for developing their vehicle. Again, this is another one of those reasons why it's really important to get a car done early. Why it's important to have a plan, a testing plan, to make sure that you can run through and validate and tune and all these other important things. They had a comfortable, clear display. Again, simple display. A number of teams try to do something really, really elaborate in terms of a dash, and while it looks cool, there's definitely kind of a whiz-bang kind of a an aspect there. Ultimately, for piloting a car around an autocross course, I mean you're turning every couple of seconds. It's a very busy busy activity. You're just not going to have the time to digest a lot of information on a screen. So a simple display is going to get you a long ways, and they did a good job of executing something that met the needs and was simple to read. Inertial mass unit data, again, utilizing sensors in order to collect data when you're out on the track. And basically, and it's probably one of the better aspects there is they were able to quickly take that data and turn it into useful knowledge for what's the next change I should make, or did I just to validate the change I made, did the vehicle respond the way I wanted it to, so again, it was a good use of data for driving tuning changes and the like. That was the last one, right? All right. So with that, let's hear it for Stuttgart. I asked. There actually was another slide. Yeah. Okay. Another aspect of the tub that we liked, and I think we mentioned this last year, but it's something that we really like, and it's just a good practice, is the use of the cup cone attachments between the tub and the rear portion of the chassis. Again, it's very useful for accurate locating. It's got good shear loading capability, and it's really not that hard to do. So again, it's one of these design details that we like. We as design judges generally like a lot of the finer detail kind of stuff. We want the fundamentals to be done right. There's no question about that. But these types of details, kind of just are what helps separate the best cars from the good cars. Again, another example of screening composites and bonding joints, X-raying joints in this case, as a non-destructive test method, for ensuring that that the integrity of the part is what it needs to be. Again, not only is this a way for preventing failures, but it's a way of just saving time. Why bolt a car apart on the car? A link or something like that that's going to fail, and you have to replace it and put the car back on the setup pad and all that. You're better off just building them parts up and testing them before you install them, and that way you're golden. I guess the last item on here, just the FEA on unsprung components. This is referring not just to the strength characteristics, but actually more to the compliance aspects. Trying to assess what the parts are going to be from a stiffness standpoint, and then putting those parts into the full system and assessing the system level compliance. Which is a word you probably heard me say maybe more times than you care, is just the whole system aspect. It's important to think of these cars not just as a collection of parts, but they're really it's a system of systems, and unless you analyze them as such, you're just not going to end up with something that's performing as well as it could as if you were trying to integrate again, here I say it again, integrate the whole system. All right, so I think I'm done here for the moment. I'm going to ask Bill Riley to come up and walk you through a couple of. Okay, all right. Let's hear it again for Stuttgart. I think Bill's just stalling. He doesn't like being in front of people. All right.
All right, the next section of the talk, we were going to move in and talk a little bit about some of the design details that we had seen this week specifically, and also from kind of the history book. So what we did is we took Pat Clark's 7 Deadly Sins, which is pretty well documented online. So everything we're going to show you now comes right off the website, and I put the URLs at the bottom of each page, and they're pretty short, so if you want to write them down. So I won't go through everything in extreme detail, but we wanted to give you a sort of a reference point to get back to this material because it's pretty good. And then what I did is I added blue boxes, so the Pat Clark content is all on the slide, and then Tony and I looked at it and we put some comments in the blue, so that's sort of us interpreting Pat's comments and also trying to make it a little more specific to this weekend at Michigan. So the first, one of the first things Pat says is basically that all things being equal, you want to reduce weight, lower the weight, lower center of gravity, and localize the weight to make the vehicle turn in better. And so, design judging, when we look at your car, we're really looking at the mass that you're presenting, both the overall vehicle mass, the unsprung mass, the rotating mass, all of the masses, and we want to see them small. And I would add another thing that we noticed this weekend is the cars are getting quite a bit physically smaller, because I think we're finding that we just don't need all of the metal that we thought we did in the old days, a decade ago. And we're seeing things get quite small and condensed, which is great. But we also want to make sure you're just putting enough cross-section in there. So for things like hubs and drive shafts, larger geometric cross-sections of thinner wall will generally win out compared to solid, smaller diameter. So I would say that's just like a thing to note from this week. When it comes to rod ends and bending, I think we've been saying it, since the Carroll Smith days. So we did see 3 cars this week with rod ends and bending. So I just wanted to really touch on it briefly. But even if you say the design judges are wrong and we like rod ends and bending and it's easy to set up, we're going to ding you for it. So you might look at the points analysis and just say we really shouldn't do rod ends and bending. And so the next slide will show why that's true. So if we have on the far right sort of what we consider a standard A-arm approach, where you have spherical bearings pressed into cups, you see the line of action is through the center line of those joints. And it's essentially becomes a 2-force member where you have tension and compression. And then when you put rod ends into bending, you end up getting a non-straight load path. So now you're carrying bending moments through the rod ends. You're putting threads in bending. And that's a really inefficient way to carry the load. It'll work. You just have to upsize the components to carry the load. But it's not going to be winning on a mass front with the other designs. Rear toe compliance. So we sort of, in case you're not aware of the toe base, the distance between the toe arm and the ball joint, we really look at this. And what you really want a wide toe base. So there's compliance in the joint, the lash, the motion at 0 force around those joints. And as you get a wider toe base, you'll have less sensitivity to that fixed lash, and the loads are generally going to go down and make it a more efficient structure. So Pat has a lot more guidance about toe base, but just know that it's really one of the fundamental things when we walk up to a car. If we had maybe 2 minutes to look at it, like when we're walking around the paddock, this is one of those things that catches our eye. Unsupported rocker pivots. So, there's not a lot of cases on the cars where single shear is a good thing. We generally drive for double shear because it gives us much lower loads and more structural efficiency. There are a few places where single shear tends to win out, such as on rocker posts, like the one shown in the picture. So single shear rocker posts is pretty, it's quite an acceptable design practice. But you do want to watch the node. So in this case, the place where the rocker's pivoting is not actually at a node of the chassis, right? There's a bit of a distance along the tube. So it's going to be less stiff and more compliant. And it's just much worse for the load paths. And then you also get a moment into the bearing system in the rocker. So again, this is just one of those very fundamental things you want to get right. Okay, tapered wheels. So there's a bit of a language here. So as I would say it, when you're designing these wheels, you can either center on the hub or center on the wheel studs. Generally, centering on the hub is a good choice. And then you have drive pins to carry the torque through the wheel, for example, in the rear. So you want to make sure you avoid sort of these stress concentrations, and the combination of the tapered lug nut into the wheel puts a stress in there that you also need to consider. And the next slide, we talk a little bit more about this. There's also this effect, which I thought was worth mentioning, where when you buy metal from the mill, it's rolled, and it actually work hardens it down, so it changes the thickness to get a thinner section. And as you look at thick plates like you use for wheel centers, the through thickness direction is weaker. So the grains from rolling actually add strength to the plate. And so when you machine a wheel center, you need to make sure you look at the properties through the thickness of the plate. It's called the ST direction on the picture. And so it's actually not as strong as the direction in the long direction of the plate rolling. So if you're seeing weird cracking in your wheel centers that you machine out of billet, or other like clevises, parts that have very high through thickness loading, you'll want to watch that and make sure you're looking at the ST strengths. And again, on this pin choice, so we saw a couple instances where teams had started with aluminum shear pins and switched to steel. And generally, the best guidance is to put the hard steel pin into the, press that into the softer aluminum. And steering geometry, Pat has a ton of information about steering geometry, which I won't read to you right now. It's all available on the website. But I also wanted to add that when you look at your steering geometry, make sure that you have enough length of brake lines so that as you steer, you're not putting tension on the brake lines. Also check that if you don't have a front wing, if you're picking up cones, you don't want to load those brake lines up as you hit cones. So we look for that in tech as well. And also, for wings and for A-arms and such, you do need to include the cone loading. So when you think of an A-arm, and I just said it's hopefully a two-force member because of the sphericals, you will get bending loads from hitting the cone. So hopefully you're thinking about that in your load cases. And cooling system connections. So I think Pat makes a good point here, which rubber is heavier actually than aluminum. So you really want to run, metallic lines for the lightest weight. You want to have the minimum amount of rubber, the minimum amount of hose clamps. All those things are heavier. Put the radiator near the engine, minimize the coolant mass, all of these fundamental things. And a thing I wanted to add is, having worked at driver change and seeing the endurance cars, you really want to make sure all of the tubes have beads at the end so that you get a good clamp up on the hose connections. I've seen countless cars also on the intake system. So basically intake systems, oil lines, coolant lines, where you just cheat it because of time or you don't think you need it, that bead, the rubber hose will pull off and it'll put you out of endurance. So you really want to, the attention to detail will keep the car in endurance. And then wheel and upright compliance. So I think we talked about all of the finalists today. Everybody's looking at compliance and making sure you're getting a really stiff design with minimum lash in the system to lead to a very stiff car. And maybe even you have a chance to measure the installed compliance on the vehicle and your installation stiffness. And expect us to, in design finals, to sort of manipulate the wheel and see how it's deflecting. It's not quantitative, but you really shouldn't see a lot of motion on the bearing system or other aspects of that. So that's Pat's write-up from the web with our little spin on it. And the next is we took some pictures and observations from the cars we saw this week. So we saw a couple cases where folks were using bolts and putting them into the hubs, which in this case, this is a good example. So by the way, I have pictures of only good examples, hopefully. So there's no embarrassing pictures coming up. But this hub was steel, so it was fine practice to put the bolts into there. But you don't want to put those bolts into aluminum hubs. You're taking them on and off a lot, and you're going to wear them out. So that's a red flag for us. Also, you may also want the wheel studs because you're going to be able to sort of use it to get the wheel on, and it's going to be much more robust in the long run. And if you are putting bolts into aluminum threaded parts over, in a place where you're taking them apart fairly repeatedly, you do want to put some inserts in there like helicoils or key inserts. And then hub fundamentals. So we did some questioning on the hub design and the bearing system and how you're preloading the bearings during finals. And one of the things we took away is we wanted to talk about it briefly. So David Gould, a longtime judge, has provided this picture generously of his GR59 hill climb car. And what it shows is that between the two bearings of the hub, so you can see the hub is white, the yellow color are the two wheel bearings, the purple is the brake, the flange for the brake rotor, the brake, and the kind of where I put the arrow, it shows the spacer. So what we think of as a traditional race car hub design, you're setting the load onto the bearing system with either a nut that you adjust the torque on, or a plate perhaps, and with a shim so that you're getting the right amount of preload. And then what we saw some teams doing, which is to put the load into the bearing system, and all of the torque on the hub nut is going through the bearings. And what that means is you're going to have a lot of sensitivity to the preload in the bearing system. And the K factor, which is the relationship between torque on the nut and the preload in the bearing system, as things change, the friction changes, you'll have different amounts of load in the bearing system. And so it's quite traditional to put a spacer in here, and we really think that's a good design practice so that you have a more controlled amount of preload in the bearing system. If you don't control it well, what you tend to do is it'll heat up due to the excessive friction, and you'll start to see funny things happen. Things will loosen up, or it'll get hot and grow the compliance. So just wanted to give you an example of what we think is a really great hub design. Okay, we did see one car. This is Cincinnati actually had this innovative design we wanted to share, which was they 3D printed the nodes of their space frame. So you can see in the picture they've masked off the frame tubes where they have the 3D printed nodes, and then they welded the steel tubes into the nodes. And I just thought that was a cool shout out for this design. And they made sure, actually, per the structural equivalency process, made sure that the node was stronger than the tube it's attached to, so it's not a weak point in the design. Brake keys. So we also saw a lot of brake keys, and I wanted to say quickly that there's a lot of great ways to do brake keys. There's not one way or another that we like or dislike. There's a few types of hardware that I think are quite poor choices. The main one is these E-clips that you see there. I think it's called an E-clip because it kind of looks like a round E. But they are not very robust and durable, and I've seen a lot of cars go out of endurance for different types of retaining ring failures on the brake keys. So we really don't support the use of the E-clips. Generally, if you're going to be using a retaining ring, I would recommend the spiral type retaining rings. Spiral Lock is one brand of those, which is shown, I believe, in the lower right. Sorry, the lower left of the 4 cluster over there. And then there are many, many other ways. All of these I thought were quite good from this week, that were ways to float the rotor so it has side-to-side compliance, but still secure it to the car. Lastly, be tidy. So we really want those brake lines, electrical wiring, all of the things that have to get from the car out to the upright to be neat and tidy. We want a car when you walk up to and you're like, oh, well, there's really nothing to this. This thing looks just very straightforward and clean. That's where we think you've done the most work, actually. So if everything's just very sensible, located, co-located together, clean, there's not a lot of exposed threads because we're talking so much about mass, so it's really hard to believe that the time it takes to cut the wheel studs off and clean them up isn't time well spent if you before you get to design with us. So the more time you spend, it'll actually make it look like there's just less to it. But we know that, and when we walk up, we're looking to see this really nice, clean layout. And wing mounts. So wing mounts, as we've looked at them over many years, there's a lot of different approaches. And the one thing I want to say is, here's an example I thought was quite good from the paddock today. And I think that it's worth, one thing is I think sometimes we let the aero guys do the structural design of the wings. So I would say treat it like the rest of the car structurally. Have a structures, type person think about it with the aero folks and make sure that it's set up from the beginning. The very design realizes what the stiffness requirements are. You want those wings to be where you analyzed them and calculated them and tested them to be, not moving all around on the track. And so we think it should be right fundamental to the design of the aero structures, how you're going to support them and minimize their motion. And with that, that finishes the formal part of the presentation today. And we were going to find out how much time we have. We are out of time. What is 4? We have 4 minutes. So we have 4 minutes, so we're going to do a few questions from the audience, if you like. So if you come up to the projector and ask the question, then we'll repeat it so everyone can hear it.
When you get done, at some point, I need Coburg and Toronto.
I'll ask them now. While we prep for questions, if we could have representatives from Coburg and Toronto, please come to the front for your presentation preparation.
No?
There's no questions.
No
That's
questions?
fine. What?
Thanks.
Oh, thanks. All right, then let's just be done.
Yeah, all right.
Great. Well, with that, no questions. Or do you have a question?
Oh. Okay, we do have a question. No, we don't have a question.
All right. Well, then we're going to say thank you so much for listening and good luck in the year ahead.